Hi there, and welcome to Telefunk In. In today's video, we're going to show you how you can fix your KORG MS-20 monophonic synthesizer for 50 cents. That's right, 50 cents. Before we start, it might be worth reflecting on the fact that KORG MS-20 was made in 1978. In 1978, Grease was the word. It was fun to stay at the YMCA, and the Bee Gees were staying alive. 1978 was the year that the Sex Pistols invaded America and then promptly broke up. Space Invaders was released, catalyzing an explosion in growth in video game arcades across the planet. You could buy a Tandy TRS-80 personal computer for $399, and computer bulletin board systems were launched, something similar to a precursor of accessing the internet using the World Wide Web. Given the state of technology at the time, it's perhaps no surprise that instruments of this vintage might occasionally fail or require servicing. The instrument that we're approaching today, we know very little about. It was purchased in non-working condition from a vendor in Japan. As such, we're going to be approaching this instrument very carefully. A typical diagnostic approach, one that could be applied to almost any instrument with a non-specific failure, is shown on this slide. We'll start with the power supply, examining the transformer to make sure that it's actually passing AC voltage, that voltage is being properly rectified to DC and regulated and filtered. Once we've confirmed that the instrument power supply rails are functioning properly, we can then begin to examine the signal path, making sure that the keyboard is actually generating control voltage. We would then turn our attention to the voltage-controlled oscillators, voltage-controlled filters, and the voltage-controlled amplifiers in the instrument. And finally, we would go through all the mechanical elements of the instrument, including the keyboard, all the keyboard contacts, the various jacks and connectors that interconnect the PCBs on the interior of the instrument. It should be obvious that in order to support this type of diagnosis, we'll need to disassemble the instrument. While there are certain operations that can be accomplished without complete disassembly, this type of component-level PCB servicing requires full disassembly of the MS-20, process that I've described on another video that you'll find on my YouTube channel. Since we'll be operating with AC line level voltages, this is a procedure that you should only undertake if you have the required experience and know what you're doing. Similarly, you do have the potential to damage your instrument, and I can't be held responsible for any damage that may occur as a result of following along with the steps in this video. So what we have here is the innards of the KORG MS-20, which have been removed from the case, the chassis, and reassembled here on my bench. And really all this is required is resoldering the power cord to the fuse connector here. And you'll recall that this is a Japanese manufactured but also Japanese marketed instrument, and as such it has the KA221 transformer and is currently wired for 100 volts AC operation as opposed to the roughly 120 volts that we have here in North America where I am currently. And I can see from the monitor on my wall that actually my voltage is 118 volts as opposed to 120 even. But that's going to vary 1 or 2 volts in either direction. So we're set up to test the instrument. The only things that are not currently connected are the modulation wheel is not connected. It's been disconnected, as has the keyboard. And the keyboard is connected with I think it's a 4-pin connector. So everything else is connected. We know that this instrument has been sold to me in non-functioning condition, and so we want to be very cautious about powering it up, in particular because it has the wrong transformer for this local voltage. So we're going to power it up using both a variac and an electronic circuit breaker to ensure that it doesn't draw more power than it should in the event that there could be something catastrophic wrong with the instrument or its power supply. I've also connected a ground lead, which normally goes to the chassis of the instrument and connects here to this assembly on this PCB. I've connected that to the ground on this circuit board, so everything has got a good ground on it. So first things first, before we bring power into the instrument as a whole, what I'll do is I'll disconnect the connection between the transformer, power transformer, and the circuit board, and just make sure that the transformer itself is functioning properly and we don't have any shorts in the transformer. So a very simple way to do that is to measure the resistance across the primary, which is simply the two connections on the plug of the instrument. So we have about 41 ohms across the primary, so we know that it's not shorted, for example. And then if we look at the secondary of the transformer, we have a secondary winding with a center tap, and we see that we have about 6.7 ohms on the secondary. If we measure across the center tap, we have about 3.56, and then the other winding 3.3938. It's not uncommon for there to be a slight discrepancy, but that makes sense. So they add up, and the overall resistance of the secondary winding is less than that of the primary winding, which makes sense because this is a step down transformer. We're going from 100 volts to approximately 18 or 20 volts on the other side. So let's see what that voltage actually is. So this is the apparatus that we're going to be using to power up the instrument, and it's this piece of equipment here in the middle of my rack here, if you will, which consists of a variac, an electronic circuit breaker, and an isolation transformer. We're going to be using all three of these. The plug on the KORG MS-20 is a non-polarized plug without a ground, and so we don't know which of these plugs would be going into the so-called hot lead on the AC. So we're going to use an isolation transformer so we don't have any surprises. And we're also going to be using the electronic circuit breaker. Now this is described in another video on my channel, but essentially what we do is we set the maximum current and the number of cycles that we'll tolerate at that current. And if indeed we exceed the settings, the electronic circuit breaker will break and thereby protect the instrument from frying itself. We'll also, the variac is currently set at 100 volts, but we'll be turning this up slowly when we turn it on. And we'll turn it on right now. And you'll notice really nothing has happened, and that's because we haven't actually turned up the variac to power the instrument. So we're now at 37 volts, and we see that we've exceeded our current setting, so I'll turn that up a little bit. So we'll set the variac at a nice even 100 volts, and it's drawing essentially minimal current, which is to be expected. And we'll check the voltage on the secondary of the power transformer and make sure it's functioning properly. So we're getting an AC voltage of approximately 41.5 volts out of the power transformer, which makes sense because we're getting approximately 21 volts into each side. Remember, this is a power supply that is going to give us 15 volts, both positive and negative, and the center tap will become our ground. So it appears as if our power transformer is operating properly. So we'll reconnect it. First we'll turn off the power, we'll reconnect it, and then we'll power up the instrument and see what's happening. And so we have reconnected the power transformer to the instrument. Come over to our variac, which is set at 100 volts. We have the variac, the isolation transformer, and the electronic circuit breaker engaged. And if I give this unit power and I turn it to 0.2 amperes as being the trigger set point at 16 cycles, and I turn on the electronic circuit breaker, what's going to happen? Well, we just tripped our electronic circuit breaker. We can reset that, and it immediately tripped again. So we need to turn up the power slightly. We'll do that. We'll turn it up all the way to 1 amp, keeping in mind that we have a 1/2 amp fuse in the instrument. And we're apparently drawing 1/2 amp and almost 50 watts. And so what's going on over here? Wow, that's getting hot. I'm turning off the power. Keep in mind, this instrument is supposed to be drawing 10 watts maximum power, and it's currently drawing 50. So something is wrong, and something is wrong with this negative rail. This is the 7915 voltage regulator, which regulates the negative 15 volts portion of the power supply. If we examine the schematic of the KORG MS-20, we see the power supply here, where the negative 15 volt supply is regulated by the 7915 regulator. And this is getting awfully hot, and we're drawing 50 watts worth of power. What could be going on here? Do we have a short in the negative supply rail of the power supply? Maybe one of these capacitors, diode shorted, for example. The answer to that question is no. I've already checked these and they're functioning properly. So something else is happening after we leave the power supply. The negative 15 volts supplies power to various portions of the circuitry, and they've all been highlighted here in orange. And many of these are on the main board, and some of these are actually on our secondary boards, the KLM 128 and the KLM 129. So this is our 129, and this is the 128. The 128 is the board that interfaces with all the external jack points, and the 129 is the external signal processor, which includes sort of a mixing section. So one of the things that we can do to help diagnose what's going on is remove these boards from the equation and attempt to identify whether or not our problem with the negative 15 volt rail is on one of these two boards, or if it's on the main circuit board, and that'll help us focus our attention and narrow things down. I would suggest that given the rather significant power draw, we probably have a short somewhere on the negative rail, and that could be many different places. Could be a shorted capacitor, could be a shorted resistor to ground. Various other things could be going on. We have a lot of potentiometers that are voltage dividers that are connected directly to either the positive or negative rail. And if any of these have inadvertently shorted to ground, we would have a short that could potentially explain our 50 watt power draw. But we'll see what's going on, approaching things one step at a time. So first things first, let's disconnect one of these boards and see what happens. Start with this guy first. He seems most straightforward. So the cord is connected through various multi-pin connectors, and they're all labeled with numbers both on the connector and on the board. So for example, this connector here has the number 2006 on it. And if we look at the board, examine the board, we see H6, which presumably stands for harness 6. This one says 2010, and we see on the board the label H10. Similarly, 2011, H11, and so on. So while it is eminently possible to mix these up and plug them into the wrong position, so for example, these two connectors are 3-pin connectors, and they're essentially interchangeable. If you pay attention to the designations which are printed on the connector and on the board, you shouldn't go wrong. So let's disconnect this board. So that's the board there. And you'll notice that these connectors are asymmetrical, where they have a little clasp, and this small clasp actually goes over a lip, which is on the inside of the board, on this particular board. And so if you keep that in mind, you won't be putting these on backwards. So we've disconnected this board. We'll power up the instrument and see what's happening to the power supply. We've got a maximum 1 amp, 16 cycles. Turn on the power. Oh, and we need to reset the electronic circuit breaker. And we've got 100 volts, and now we're down to 0.1 amp, i.e. almost exactly 10 watts, which is exactly what the instrument should be drawing. So that is highly suggestive. It suggests to us that our issue may be on the board that we've disconnected, since the power supply seems to be behaving properly. Let's come over here and examine the regulator. This regulator is not getting hot. We'll actually measure the voltages out of these regulators and see if they're performing as they should. So this chip here is our positive regulator, and we measure from pin 2 to pin 3, and we see that we have 15.2 volts. This is our positive 15 volt rail, and it seems to be performing as it should. This is the negative voltage regulator, the 7915. That was getting very, very hot, and in order to measure its voltage, we measure from pin 1 to pin 3. And this is giving us negative 15.04 volts, which is exactly right, and it seems to be keeping cool. And again, that's highly suggestive that the problem is not on this board, and the voltage regulator seems to be working just fine, which is great news. So it looks like we have an issue with this board and potentially a short to ground on the negative 15 volt supply. So let's have a closer look at this board. If we examine the schematic for this board, and again this is the KLM 129 PCB, and in particular we're looking at a KLM 129B, revision B presumably, and the date on this board, I don't know if you can see that, it's 1978, second month, 16th day. So isn't that kind of interesting? See, this board was made all the way back in 1978, or at least designed in 78. If we examine the schematic, we see that the power supply for this board is here. The voltages are coming in on pins 9 and 10 with a ground on pin 11. We have two 100 microfarad at 16 volt capacitors on the power supply. And even though these are indicated as being before the pins, they're actually located on this board. So that's a little counterintuitive. After the negative supply reaches the board, it's then involved in powering this TLO81 and another integrated circuit, an op amp, which is a 339. And there's a 4558 on the board as well, at least one. So what happens if we examine the board and measure across pin 11 and pin 10, which are up in this corner here of the board? So this is pin 9, this is pin 10, and this is pin 11. 11 is the ground, and 10 is our negative 15 volt rail. And we have a short. There we go. We have a short between pin 10 and 11 on this board. So that's bad news, we need to fix that. What would be a likely candidate? Well, if we flip the board over, we see these 100 microfarad capacitors that I was talking about. And yes, indeed, there's one right here across the ground and the negative supply rail, which is measuring as a short. Let's remove that capacitor and see what's going on. Power up our soldering iron. This will be very old solder. So perhaps the best way to get this solder to flow is to add new solder. So simply by heating up each pad individually and rocking the capacitor, we can remove it from the board. There we go. There's our capacitor. And we seem to have addressed our short. So let's measure across this capacitor. Yeah, we've got a shorted capacitor. So what is this? This is looks like a Matsushita 100 microfarad at 16 volts. 16 volts. A lot of the electrolytic capacitors in this instrument are rated very, very close to the operating voltage. So this 16 volt capacitor is meant to filter a 15 volt supply rail. And 16 volts is a little too close for comfort in my books. So we'll replace this with something a little better. So I have desoldered the capacitor and cleaned the board a little bit. As you can see, these old KORG boards are covered with this sort of varnish stuff that looks a little bit like flux. We'll clean all that off a little later as we go about the refurbishment of the instrument. But this is good enough to get a good solid connection. So I'll be replacing this capacitor with, which is a 100 microfarad 16 volt, with one of these, which is also 100 microfarad, same capacitance, but a 50 volt. And accordingly, it should be much more able to withstand the voltage that is provided to it. There's plenty of room on the board. In fact, it almost looks like the board was designed for this size of capacitor. It fits in perfectly right next to its partner on the positive rail. And I'll insert it, bend the leads a little bit just to keep it there. And regale you with my soldering technique. Heating the pad first and using the heat in the pad ideally to melt the solder as opposed to the soldering iron doing the work. Of course, that's a mighty big pad, given that it's I believe a ground. There we go. Clip these. Measure across and make sure we no longer have continuity. Correct. We have, in fact, an overload. And now we'll reconnect all these connectors. And again, the connectors go into the board with this little clasp facing inwards. And it becomes obvious if you just inspect the geometry of the connector. Apparently easier said than done. There we go. H12, 2012. Okay, so that's this board. KLM 129 connected, reconnected. And we'll now power up the instrument and see what happens. Again, we're using our Variac here and the digital circuit breaker. And we've got 11.3 watts now. Still reasonable relative to the 50 watts that we were showing earlier. Let's see what we get on the power supply. "15 volts on the positive and negative 15 on the negative rail." And this regulator is not getting hot. So it appears we may have just fixed our MS-20 with a 50-cent part, which would be fantastic. So what to do now? Well, while we're in here, as they say, given the fact that we've already had a failure with one of these electrolytic capacitors, it might make some sense to actually think about replacing all of them. And that would include these two big ones, the 1000 microfarad at 35 volts and this 470 at 25 volts that are part of the power supply filtration circuit. But other than that, there's actually really not that many electrolytic capacitors on this board. There are a few tantalums, and I'll be replacing those as well because they're prone to catastrophic failure, usually failing in a short mode. And we'll go from there. Well, as it turns out, that really did fix it. That brought the KORG MS-20 back to life. What we're looking at here are the various schematics that make up this instrument. There are 2 pages of schematics in the service manual, and then on the bottom half of your screen you're looking at the schematic for the KLM-307A, which is the OTA filter board mounted on the back of the main KLM-127 PCB. We started off with a fault that we found in the power supply where the power supply was drawing 50 watts. And we located the source of the fault, which was on a completely different board, KLM-129, and actually was one of the capacitors meant to filter the incoming power to that board. The way we approached this was kind of a divide and conquer approach. By pulling off the PCB, we were able to isolate the fault to that circuit board, and frankly, the very first component that we looked at was the one causing the problem. And what you've seen is exactly what played out for me in real time. I've edited this video down for the sake of brevity, but I might have spent a total of an hour working on the diagnosis and the repair, and that included all of the filming and manhandling 3 cameras. The thing about working with vintage electronic instruments is oftentimes a low-tech approach will be adequate to facilitate a repair. The divide and conquer approach that we used, separating the individual PCBs, is a helpful place to start wherever possible, but oftentimes instruments aren't constructed in a manner that will facilitate this. You can, however, look at the various controls on the instrument, and sometimes simply by turning a potentiometer up or down in one direction will effectively isolate one part of an instrument from another. In the absence of fancy diagnostic equipment, use your senses, your eyes, your nose, and your ears. One of the most common causes of failure of electronic components is thermal overload, overheating, and oftentimes components that have been stressed in this way will be swollen or actually burned, or they'll just simply smell really, really bad. In some cases, components that are undergoing high-frequency oscillations will actually hum or buzz when they're under power, and you can use that to isolate the source of the problem. In some cases, when you have an instrument powered up, again, assuming it's safe to do so, You can tap, freeze spray, or even press on the PCBs or their components to identify intermittent faults, or simply touch them and see which ones are hotter than they should be. In addition, some components are known to fail more frequently than others, electrolytic capacitors being quite famous, tantalum capacitors being another component that fails quite frequently. And knowing which ones fail more frequently than others is, well, I guess that's experience. And this brings us to the next point. The title of this video suggests that we're able to repair the MS-20 for 50 cents. And really, that's the cost of the single part that went into the instrument, or at least the part that was necessary to facilitate the repair. I'm going to go on and fully recap this instrument, removing all the electrolytics and the tantalum capacitors, and even change out a few other components that I think would be wise. I'm replacing the power transformer with one that's suitable for North American voltages, and I'll be putting a fuse socket on the rear panel of the instrument as well. The disassembly time alone was at least an hour on the bench, and I don't think that it would be much shorter if it were a more experienced technician working on the instrument. The schematics and the service manual are available free online, and the diagnosis and repair time that I mentioned earlier took about an hour or so. However, experience and prior knowledge, even negative information, is priceless information. And in this case, I'd have to suggest that I got lucky, but this is really what you're paying for when you're working with an experienced technician, is all that experience and their prior knowledge. So by all means, I wouldn't want to discourage anybody who's got a vintage instrument like this one from seeking the guidance of an experienced repair technician if you ever have problems with your instrument. So I hope this has been informative, that you've enjoyed watching, and I'd like to thank you for watching and have a great day.